So now that we've been discussing the closed loop transfer function and looking at the response of the closed loop system, let's talk about how to select a controller. Now in this class we're going to be talking about lots of different controllers. We're going to start off with what we call a PID controller, so proportional integral derivative. And you'll find that we can mix and match these different components to create a controller that effectively does what we want it to do as far as controlling the system. So let me go back to the physical system. This again is the linear servo-hydraulic system that we have in the lab, and we're trying to control the position of this mass moving back and forth. We developed the block diagram of this system previously, and you'll notice that I've added a couple of blocks to this, or a couple of summing blocks that we did not have before. The summing blocks that I've added is one right here to add in a disturbance, and you'll say, well, what's a disturbance? Imagine that I am increasing the frictional force on this mass that's moving back and forth. Or perhaps I'm leaning on it right now and not leaning on it at another point in time. These are all disturbances that are being applied to the plant or to the physical system that are disturbing how it would normally behave. So those are disturbances, and we can simply add those in. And then I'm also adding noise. What noise is simply either it could be mechanical noise or electrical noise. Very often it is electrical noise at high frequencies from fluorescent lights and other things in the area. But we'll be adding noise, and where we normally see this in the system is in the sensor data. And so I add it right here from the output, between the output and the sensor, and so our LVDT would be seeing this electrical noise and feeding that back in and comparing that to our reference signal and giving us noise that gets stuck into our controller. So we have to manage both of those terms as we're developing our controller. So what is the goal of a controller? The goal of a controller is that the output Y should ideally track the reference and ignore both the disturbances and the noise in the system. Sounds pretty simple, but that's not quite as easily as it sounds. Now, one thing I want to make a note of is that the noise that I was talking about is typically very high frequency. And because of that, if we apply a large amplification to our controller, we are going to amplify that high frequency noise. And so very often what we want to do here is we want to achieve the specifications of the system, but make it no faster than that, because then we'll start amplifying this noise. So we've got these trade-offs that we need to make as we're designing our controllers. So I mentioned that we're going to start with PID controllers. So what is a PID controller? Well, what I'm showing here is, first of all, for some arbitrary error. Remember, error is just looking at what is my reference signal minus the output. So what's the value that the LVDT is saying the position is actually in. For some arbitrary error signal that I have plotted in blue right there, I can apply a gain to that error, and I can feed that in as my control system. We call that proportional. Or I could take the integral of it, which is the red line here, and I could apply a gain to that and feed that in as the control input. Or I could take the derivative of the error, this green plot right here, and I could feed that in as input. So either one of those or combinations of those three are what I'm going to use as control inputs. Now, how do we do that, or how do we mix and match these? The first is that you will almost always include a proportional gain in the system. And this is really the standard action where I'm saying I have some error and I'm going to multiply that error by some value, and that will be going into my controller to improve the system position or whatever it happens to be. So this will decrease the steady state error, and it will also increase the speed of response. As you can imagine, the higher that I increase this gain, the faster the system is going to respond, and that's why I don't want to turn this up too high, because that's when I'm amplifying that high frequency noise and I'm going to get jittering in my system. How about the integrator gain? Well, the integrator gain is going to further decrease the steady state error because, again, I was saying this is going to integrate over time. So integrates and eventually reduces that steady state error to zero ideally, but sometimes not quite to zero. The other thing it will do is it will slightly destabilize the system. So we're going to find that integrator gain can cause system stability issues, and we can become unstable, and we'll see that from a pole placement standpoint in just a little while. The other control option I have is having a gain on the derivative of the error, and this increases the speed of response. And you say, well, why does it do that? Well, notice that this derivative is really leading the error itself. And so I'm taking the derivative of it and I'm getting very fast response, and that's why it speeds up the response of the system. it also acts as a stabilizing or a damping type of a term in my system. So I trade off these three as I construct my controllers. So what does this look like? Well, in the time domain, I have this up here where what I'm going to be doing is taking my error term, multiplying it by Kp, that's the proportional gain. Then I'm going to be having an integral term and multiplying that by the integral of the error, and finally taking the derivative of the error and multiplying that by Kd. Now if I want to put all this into the Laplace domain, it looks something like this, where I have the same values, but just now the integrator is 1 over s and the derivative is just s. So these are then what we're going to put into our system, and very often we're interested in expressing this as a controller output. So usually our C of s, this is equal to U of s divided by E of s. And I think you can see how you can fairly easily divide that out and write out that equation. But that would be what's in the controller itself when you have a PID controller. So now that I've created a controller or some form of a controller, how do I determine how well it's working? One way we can do this is through error analysis. And the idea of error analysis is saying, at steady state, how much error do I have for various inputs? And so I can look at it with respect to the reference tracking, or looking at it with respect to the disturbance or things like that. So what I'm going to do is first of all simplify my block diagram. And what I've done is I've gotten rid of the noise for now. Let's say that I can filter a lot of that out and not worry about it. I'm also going to set h equal to 1 just to make my life easier. So that's the sensor gain. And now I'm going to generate these transfer functions, and you'll be doing this as an exercise in class, looking at the error with respect to the reference. So this is just error divided by reference, and the error with respect to the disturbance. So we can think about the disturbance as being an input to the system as well. And you'll notice that in these transfer functions, as well as a lot of others we can generate for this system, such as that closed loop transfer function, we always have the same denominator for these. So that's an important piece of information as we start to understand how these systems behave. So I've generated these transfer functions. What do I do with them? Well, let's say that I'm interested in the steady state error of the system, and perhaps I'm going to have a step input for my reference. So at time equals 0, I'm going to step my reference, and I'm going to look at what does the final value of the system end up at? How much error do I have at the end of time? And the way we can express this is with the final value theorem. And the final value theorem simply says that E and infinity there is just saying that when time goes to infinity, this is equal to the limit as s goes to 0 of s times E of s. So what do I mean by that? Well, it looks something like this for a given input. Let's say that I'm looking at the error with respect to the reference, and in that case I could say E as time goes to infinity, this is just equal to the limit as s goes to 0. And now I'm going to multiply s times what I have for a value of E of s, which in this case is going to be 1 over 1 plus C of s times G of s. And then I'm going to also need to move R of s over to the right-hand side, because you'll notice that it is right here. So that's coming up into the numerator on the other side, and I get multiplied by R of s. So if I had a unit step, this R of s would be 1 over s, and that would be canceling out with the s that I have in front, and I would then be evaluating what the value of this is as s goes to 0. And this would tell me how much steady state error I have of the system. Now we're going to do this for a variety of inputs at both the disturbance and at the reference, and this will be one of the ways that we're going to determine how well does the controller we've built actually track the system, and what's its performance with regard to or with respect to other controllers that we can use.